Hello APC Mechanics students, in Unit 2, Newton's Laws of Motion, Class 1 Forces, Part 1. Then Section 1 Force. A force is a push or a pull on an object. Its SI unit is in newtons, capital N. It is a vector quantity. Forces can be classified as action at a distance field forces or contact forces. Mainly the three forces that act at a distance are given by the gravitational force, electric force, and the magnetic force. And all other forces, with no exception, would be classified as contact forces, in particular tension, normal push, friction, drag force, muscular force, etc. All contact forces are variable forces, that is, the magnitude and the direction may change from situation to another. We know that the force is a vector quantity, then it is characterized by a magnitude and a direction. By that, contact forces are variable forces, which means that the magnitude and the direction may change from a situation to another. Section 2, gravitational force. Any object having a mass m placed in a gravitational field G will be submitted to a gravitational force given by, then let's suppose this is an object and it has a mass m, then it will be directly submitted to the pull of gravity. The pull of gravity would be acting on the center of mass of the object, then we represent the pull of gravity from the center of mass. Now this object is submitted to the pull of gravity because it's being placed in a gravitational field G, and we know that planets create this gravitational field G. The pull of gravity is given by m multiplied by g, where fg is the gravitational force. Its unit is N, capital N for newtons. M is the mass of the object, given by kilograms in the SI. G is the gravitational field strength or acceleration due to gravity, newtons per kilogram or meter per second square, as we have seen in Unit 1. The gravitational field G is considered to be constant near the surface of a planet. In particular, near the surface of Earth, G is given by 9.81 meter per second square, or we can consider it to be 10 meter per second square. The pull of gravity is a field force, action at a distance, and always point downward toward the center of the planet. The gravitational force varies from place to place, while the mass m remains constant everywhere. Pull of gravity, gravitational force, and the weight are all different names for the same force, which is the gravitational or the pull of gravity. Now section 3, the normal push. Then this is the first force, which is a contact force, a variable force. The normal push Fn or capital N, or the normal reaction, it is the force exerted by the support on an object. Now suppose here we have a box placed on a support. For sure, because the box has a mass, it will be directly subjected to the pull of gravity. Now let's ignore gravity, because here we have a support, or let me repeat and say the box is at rest. It will be submitted to the pull of gravity due to its mass, but because the box is not moving, we need to explain this at the level of forces. Then it is prevented from being falling down due to the support, but we need to explain this at the level of the forces. Then we will say that there is a force exerted by the support on the box, which is the normal push upward. Then whenever we have a support, we have a normal push. What are the characteristics of the normal push Fn? The normal push is a contact force. It is a variable force. Then its magnitude and direction may change from situation to another. The direction of the normal push is always perpendicular to the support, and notice that here I have represented the normal push to be perpendicular to the support. Then whenever we have a support, we have a normal push. If we don't have a support, then we don't have a normal push. Now in the following examples, we have a box in contact with the support. Let me say this is 1, this is 2, this is 3, this is 4. In examples 1 and 2, the support is being a ramp. In 3 it is a wall, and in 4 it is a ceiling, and we need to represent the normal push in each of the following cases. Remember that the normal push is perpendicular to the support. Then in this case it's gonna be like that, and in this case it's gonna be like that. Now for the wall, remember the rule that we're following is that the normal push is perpendicular to the support, and here for the ceiling, the normal push is being perpendicular to the support, which is the ceiling. Here we're only representing the normal push on the box. Now section 4, the tension force. The tension force, Ft or capital T, it is the force exerted by a string, rope, cord, or spring on an object. Now here in the following case we have a box attached to a rope and the other rope is connected to a ceiling. Then what are the forces acting on the box? For sure, if the box have a mass, it will be subjected to the pull of gravity, but notice that the box is not falling down because due to the presence of the rope is connected to the box, but we need to explain this at the level of the forces. Then we'll say that there is a tension force exerted by the rope and the box. Characteristics of the tension force Ft. The tension is a contact force, it is a variable force. Then its magnitude and direction may change from situation to another. The direction of the tension is always along the string, away from the object. Now notice here I have represented the tension force in such a way that it is away from the object and it's along the string or the rope. Then each of the following examples we have a box connected to a rope and we need to represent the tension force, only the tension force. We're not interested in representing other forces. For example, here because we have a support, then the box will be submitted to the normal push, and for sure we have the pull of gravity in each of the following examples. Then let me say that this is 1, and this is 2, this is 3, this is 4. The tension force is always represented from the point of contact between the box and the rope and along the string away from the box. Then it would be something like this. Similarly in example 2. Now in example 3, it's gonna be along the rope away from the object. And in example 4, it would be along the rope away from the object. Now section 5, projection of a force. It is essential to decompose a vector into its horizontal and vertical components. We have seen this decomposition in projectile motion and we will review it here again for forces. Then basically the decomposition work or the projection works for any vector. In unit 1 we have seen this decomposition or the projection for velocity vector at the initial instant whenever the projectile is being launched with an initial velocity. We're gonna see here again the projection but for forces. The rule is that for a given force F making an angle theta with the horizontal or with the vertical, one of its component will be F cosine theta and the other component is F sine theta. Let's consider example 1. Here we have a force that exists in an xy plane. Theta is the angle between the force and the horizontal. Then in this case the horizontal component would be F cosine theta. So whenever theta is the angle between the force and the axis, then the component of the force along this axis would be F cosine theta and the other component would be F sine theta. Then let me repeat and say F makes an angle theta with the x-axis, then the component along the x-axis would be F cosine theta and the other component would be F sine theta. Now why, if one of the components F is cosine theta, the other component is F sine theta? Because we know that Fx and Fy are partly from F, and if we add them again we need to get the capital or the big F, and this can be done using Pythagorean sum, which is given by capital F is the square root of Fx square plus Fy square, which is the radical of, then Fx is given by F cosine theta, then that would be F square cosine square theta plus F square sine square theta. Now if we factor out F square, that would be cosine square theta plus sine square theta, and we know that this is equal to 1 for the same angle. Then we're left with the radical of F square, which is capital F. And for this reason, whenever one of them is cosine theta, the other should be or must be sine theta in order to ensure that the Pythagorean sum would give us again the capital F. Another example, example 2, determine the horizontal component Fx and vertical component Fy of F in terms of F and theta. Here, F makes an angle theta with the vertical, then the vertical component would be F cosine theta and the horizontal component would be F sine theta. Example 3, determine the horizontal component Fx and vertical component Fy of F in terms of F and theta. Theta in this case is the angle with the vertical, then Fy would be F cosine theta. But notice that in this case F is in the negative direction of the y component, then that would be minus F cosine theta. If Fy is given by cosine theta, then Fx, if given by F sine theta up to a plus or a minus sign, since F is pointing along the positive direction of x, then that would be plus. Example 4, we need to find Fx and Fy. Theta is the angle between F and the vertical, then this is gonna be F cosine theta up to a plus or minus sign. Because F is pointing in the positive direction of y, then that would be plus. The other component would be directly F sine theta. Because F is pointing in the negative direction of x, then that would be minus. Example 5, and this example is very important because this will be representing the motion of an object along a ramp. Here they have provided the angle theta to be the angle of inclination of the ramp. Then let's do some work related to the geometry of this triangle. This is a right triangle. If this is 90 and this is theta, then that angle would be 90 minus theta, because if you add up these three angles, theta plus 90 minus theta plus 90, this would cancel, and that would give us 180, which is the sum of a triplet of angles in any triangle. Now if this is 90 minus theta, then that angle would be theta. Let me repeat and say, you can take it as a general rule. If the angle of inclination is given by theta and F is a vertical force pointing downward, then this angle here is given by theta. Why this is important? Because this is gonna help us in projecting F along the y-axis and the x-axis. Here I will refer to this as the y-axis and to this to be the x-axis, and not the vertical and the horizontal. In this case, theta is the angle between F and the y-axis, then Fy would be F cosine theta up to a plus or a minus sign. It's pointing in the negative direction of y, then that would be minus. And Fx in this case would be directly F sine theta. And F is pointing in the positive direction of x, then this is plus. Section 6 FBD, free body diagram. The free body diagram, FBD for short, is a sketch of the forces acting on a specified object. The FBD is a crucial technology for analyzing forces and to deal with the Newton's laws, as they are vector equations. What are the rules for doing the FBD? Rule 1, the object is represented by a dot. Rule 2, each force is represented by a distinct arrow starting on and pointing away from the dot. Rule 3, we do not draw the component of the force, no projections are done at this stage. So this rule is very important, rule number 3. We know that a force can be projected into its component. Whenever we're doing an FBD, we do not represent the component or the projections of the force. Example 6, an object is placed on a level surface. On the dot below that represents the block, draw and label the forces, not the components. Now in the AP exam, they will explicitly specify for you that you should draw the force and other components that act on the object. Each force, so basically the first sentence would be rule number 3. Each force must be represented by a distinct arrow starting on and pointing away from the dot. This is rule number 2, and they will represent for you a diagram which represents rule number 1. That is, the object will be represented by a dot. Now what are the forces acting on this object? We suppose that the object has inertia, which is the mass, then it will be directly subjected to the pull of gravity. Because we have a support, then it will be subjected to the normal push, which is acting upward. And notice that in this case we have represented the pull of gravity and the normal push to be equal in magnitude, because the object is said to be at rest and the forces are balanced forces. Example 6, a block is attached to a cord. On the dot below that represents the block, draw and label the forces, not the components that act on the block. Basically this is rule 3. Each force must be represented by a distinct arrow starting on and pointing away from the dot. This is rule number 2. And rule number 1 is represented here, that the object is being represented by a dot. We need to represent the forces. Because we suppose that the block has a mass, it will be directly subjected to the pull of gravity down. And because we have a chord, then there will be the tension force, which is up. And here in this case we don't have a normal push because we don't have a support. And notice that we have represented the pull of gravity and the tension force to be equal in magnitude because we suppose that the block is at rest or at equilibrium. Exercise 1. The acceleration due to gravity on the surface of the moon is about 1/6 of that on the surface of Earth. An astronaut weighs 600 newtons on Earth. The astronaut's mass on the moon is most nearly. Then they're asking for the mass of the astronaut. We know that the mass is always the same everywhere. Then basically we have the weight of the astronaut on Earth. We can directly determine his or her mass because we know that the pull of gravity is given by m multiplied by g. We're interested in determining the value of m. Then m in this case is given by the pull of gravity divided by g. The pull of gravity is given by 600 newtons and g is given by 10 newtons per kilogram near the surface of Earth. Then that would be 60 kg, and the correct answer in this case is D. Exercise 2. A block of mass m is initially moving on a rough surface inclined at an angle theta above the horizontal, as shown in figure 1. Then basically in figure 1 we have a block of mass m initially moving down the ramp. This is the velocity vector. Figure 2 shows the 4 forces acting on the block. Which of the following best describes the motion of the block at the moment shown in the 2 figures? So we know that the block is moving down. We can directly eliminate A and B. But whether the block is moving down, speeding up, slowing down, or a constant speed, this is related to the direction of the acceleration. If the acceleration is 0, then it's moving at a constant speed. If the acceleration down is speeding up, if the acceleration up is slowing down. And we know that the direction of the acceleration, as we shall see in Newton's second law, that it's related to the direction of the net force. And this can be done by referring to the FBD in figure 2. Now here, this force can be decomposed into 2 forces. Now we suppose that the vertical component of this force would cancel with this force. Then these 2 cancel and we are left with the horizontal forces, which is 1, 2, and the horizontal force of this one. Now basically here, this can be replaced by another force along the horizontal. Now if you try using a ruler to add the forces horizontally 1 and 3, you will notice that 2 in magnitude is greater than 1 and 3. Then all of this FBD can be replaced by a single force acting up the ramp like this. And the magnitude of this force would be the difference between 2 and 1 and 3 combined together. As you can notice that in this case the acceleration is acting up the ramp while the velocity is down the ramp. Then we notice that it's slowing down. Then E would be the correct choice. Exercise 3. The figure above shows the direction and relative magnitude of all 3 forces that are acting on the object. Which of the following best shows the direction of the object's acceleration? The direction of the object's acceleration is related to the direction of the net force. Basically, let me name the forces to be 1 and 2, 3. We have one force acting up and one force acting down. They cancel in a sense that they can be replaced. So first of all, let me say that we have a force acting to the right. This cannot be cancelled because there is no other force acting to the left. 1 and 2 combined can be replaced by a single force acting up because 1 is greater than 2. And in this case, we know that these 2 will be added up and will give us a net force in the following direction, upright. And in this case, because 1 in magnitude is greater than 2, you can compare them using a ruler. And in this case, the acceleration would be given by A. Exercise 4. A ball is thrown and follows a parabolic path as shown above. So this is a projectile motion, and we know that along the projectile motion, the acceleration at any point along the trajectory is always pointing down. Air friction is negligible. Point Q is the highest point on the path. Which of the following best indicates the direction of the net force on the ball at point P? That would be D, because we know that acceleration and net force has the same direction. So at any point, if acceleration is pointing downward, then the net force would be pointing downward. Exercise 5, which is the exit ticket for today's video. The figure shows a box on a horizontal surface. Which of the following free body diagrams could be correct if the box is moving along the surface to the left with decreasing speed? So the direction of motion is to the left, because with decreasing speed, then the acceleration must be to the right. Now, for this reason, forces up and down should cancel. Then we can directly eliminate this. Now here in this case, we can notice that forces up and down cancel, left and right cancel, and this is supposed to be either at rest or moving with constant velocity, but we know that it's decreasing, then it's accelerating. This can be eliminated. In order to be decreasing, then the direction of the acceleration should be to the right, which makes A to be the correct answer, because in this case the net force would be pointing to the right because 1 is greater than 2 in magnitude, and all of these 4 forces can be replaced by a single force smaller in magnitude relative to 1 and 2, or equal to the difference between 1 and 2 and pointing to the right. Then that's it for me in this video, guys. See you soon in a new one.